Alright, so we are looking at solution for problem 1 of homework 6. Let's start off with part A. So here they're asking us to compute the resonant frequency of this particular system. They have given us the bulk modulus and the volume V1 and V2 for the two chambers, and the mass m is connected to this piston rod. So let's first just write down the formula for bulk modulus. As you guys know, this is given by the change in pressure divided by the change in volume per unit volume. And if we simplify this a little bit further, delta V here in this case would be negative AP times delta X. So that's the change in volume divided by PL. AP here is the cross-sectional area of the piston head as it has been given. So rearranging this gives us formula that looks something like that. Now let's try to find out an equivalent kind of mechanical system for this hydraulic one. And that is what this system here denotes. So the spring over here kind of is similar to the hydraulic chamber here. This chamber will also push and pull this piston head based or similar to that of a spring, and same here for the second chamber, which is behaving like the second spring that's connected on the other side to this mass. And say that's our coordinate system. So if you were thinking of this mass moving, let's say, in the positive x direction, this spring over here would compress and it would push it back. On the other hand, this spring over here, this one would expand, and so it would pull the mass back to its original location. So both of the springs would have forces in the same direction, and we can write down the governing equation for this that would look like that. Right? And if you were to simplify this, you can see that we can model these two springs together in such a way that they have an effective spring constant that is just the sum of both the spring constants, right? And as you guys also know from lecture 2, the natural frequency for such a system can be given by the effective spring constant divided by the mass. So we use that formula once again over here, and you will see that we end up with this expression for our current system as well. Now the question is that what is K1 and K2? So if you were trying to find out the analogous value for a hydraulic circuit, this K1 would be represented with a formula that looks something like this. It would be your bulk modulus times the cross-sectional area whole squared divided by the volume of that particular chamber. And so similarly we have K2 as that term over there. And so we can plug both of these in, and you will finally end up with a expression that looks something like this. Now this here obviously is the natural frequency, and what they're asking us is the resonant frequency. And we can kind of see that in this particular case, our resonant frequency is equal to the natural frequency, because the actual entire formula was something like this, where our damping factor is being multiplied, but in this system we don't have any dampers, so since this is 0, this entire term goes to 0, and then it's multiplying with just root 1, so which is just the natural frequency. Let's move on to part B now. So for part B, they're saying that what would be the minimum value of the resonant frequency, right? So how can we find that? We can find that out by differentiating the expression for our natural frequency with respect to one of the volumes. So what we are going to do, first of all, is write down an expression for the natural frequency just in terms of uh, one variable, and let's pick that to be v1. Okay, so what we can do is we can use the relationship that they have given here, that v2 can be written as v minus v1, and this v here is a constant, right? So we have an expression that looks something like this. One by v1 plus, now v2 I'm writing down as v minus v1. And if you were to simplify this a little further, we will end up with a term that looks something like this. So I've just added up these two fractions basically in the second term. Now let's find out the derivative of this with respect to v1, and when we differentiate this and set the derivative to 0, that will give us the minimum value for the resonant frequency. We want to set this to 0. This is something that we want to set it to. And the expression that we would want to set to 0 would then be, so if we were to differentiate the above expression over here with respect to v1, we finally end up with an expression that looks something like this. So we are just kind of using the chain rule and then differentiating each of the terms one by one. If you guys have any issues or do not follow the steps taken at any point, or the chain rule seems confusing, you can let me know and I can help you out with that. And finally, the simplified kind of simplified expression looks something like that. Minus v1 cube, and this is multiplied by a factor of v minus v1. So what we want to do, we want to set this entire term over here to 0. And to do that, you can see that we would essentially have to set this term to 0, the term inside the bracket here. This essentially will not be set to 0 because all of the constants that we have in the numerator are constants that are given, and they are non-zero. So we have to set this relationship over here to be 0. And so what we will have is essentially that v1 minus 2v1, wait, I think I have, yeah. So we would have v minus 2v1 is equal to 0, implying that v1 is nothing but v by 2. So we plug in this, we plug in the term for v1 and v2 as v by 2. So this would also imply that v2 is equal to v by 2, and therefore at v1 is equal to v by 2 and v2 is equal to v by 2, we have our frequency as 4 beta ap squared divided by mv. There you go.